We're
Okay.
live.
Hello, everyone. I'm going to go over some things that I've already explained to some of you, but many of you may be still facing this issue of the P delta. There are different ways in which we can think about P delta and how to take it into account in a preliminary design. And so, I'm going to, let's just say that we have a column that, or this can really be a story. And let's say that it's subjected to a lateral force V, and as a result of that, it's going to displace a certain displacement, which is going to be delta. And let's say that that story has an interstory height of h. So what we are interested in sort of what that story is going to feel, and it's going to feel a moment here, and let's just call here that moment total. And that moment is going to be made out of two parts. One, we can call it sort of the primary effect, which is the product of V times H, and it's trying to rotate this, and let's just call this the primary moment. And then we're going to have another one, which is the result of having an axial load on that story, and it's been displaced at delta. So we can call that the secondary moment. And one way of thinking about P delta is to say, well, is there a way of simplifying or having like an equivalent lateral load that would produce the same effect? And by the same effect, I'm referring to the same displacement and the same moment as being produced by these two forces. So let's just call that sort of imaginary or equivalent shear force, like V with tilt. And then that would be like saying, can I have something that will produce exactly the same moment, but now with this imaginary or equivalent shear force? But we're just not going to sort of think about P delta, and then all of our equations and things that we know without P delta in that preliminary design can work. So this would be just a V acting at a given H. And then we say, okay, so if that's the M total, we would try to figure out, well, what would that V tilde would be? And it would just basically be this thing divided by H. So it would be this direct, or primary again. But then we would need to add this P delta, which is a moment, but we divide that moment by H, and this would be like a secondary force. Now I want to emphasize that this is not, it's not really, there's not going to be an additional force there, but it's just like an imaginary force that will produce such that will now produce the same moment and same deformation. The one way of visualizing this would be to say, if I have here the deformation, the lateral deformation, and this is the shear, and I have some stiffness K in my structure, and it would be sort of the conventional stiffness that we're computing with those approximate equations that don't take into account P delta, they don't have a geometric stiffness. And we say, if I just consider the V, I would be producing this displacement. Let's just call it delta 1. And then what actually happens is that then there's this like additional shear, and the difference between these two would be this P delta over H. And because there's that additional shear, then there would be another delta which is larger. So this amount over here, there's going to be an additional displacement that will take place as a result of the P delta. So we want to get a feeling of how large or small there's going to be that increment there. So one way of thinking about this is to say, okay, can I just normalize this force by V to figure out sort of like the increment? And then that would be 1 plus P delta over VH. And this term over here, it's really become like how much larger is going to be this displacement that is produced by the P delta. This little ratio over here, which if you think about it, it's a ratio of moments. And it's the ratio of the secondary moment to the primary moment. But this ratio is what we refer to as stability coefficient. Actually, in codes, we are not allowed to have this being very large. We want to keep this number low. And the typical number that building codes use is that this needs to be smaller than 0.1. That already gives you an idea that this additional displacement that could take place, well, it's essentially like about a 10%. So something that you can do as you're doing the preliminary design is to say, well, I'm going to, whatever displacement I'm computing without P delta, I'm going to apply by 1.1, but that would be really the limit. The actual, how much larger, it's going to depend on how large is your P and how large is your delta. And then what is that product relative to the direct or primary moment. Now, so that's way of thinking about P delta as if there was this additional force. Now, another way of thinking about this is as follows. To say, well, there's really, I can assemble my stiffness matrix and let's just call it K, which would be equivalent to that lateral stiffness that we are computing with those approximate equations. And if I were to apply that again with the V, I get this delta 1. And we could call it the primary displacement, the interstory drift. But then when we tell ETABS, we say, just click. I want that you do an analysis with P delta analysis. Typically what we use is this geometric stiffness that will result in, we can call, I don't know exactly the notation that Professor Dierlein uses in class, but I'm just going to say sort of like the lateral stiffness of the structure without P delta, and then we say plus a geometric stiffness. And this geometric stiffness actually ends up having a negative sign. So it's something that is going to take a little bit of stiffness away from our structures. So this will be the K minus the KG or plus, depending on how you think about this. But then this is more like what it actually really happens, is that there's this shear, but now since we have a little bit smaller stiffness, it will produce a little bit larger displacement. So there are two ways of getting the same thing, either thinking of the actual shear that is taking place, but as a result of a smaller stiffness, you get this displacement, or thinking as an extra force. So this, in your preliminary design, it basically means that if you use the equations exactly like we saw in class, you would compute what is the required moment of inertia to control the drift to this number. So there are two ways that you can do. You can use that equation, but then check with a displacement that is going to be a little bit smaller. And then how much a little bit smaller is like, instead of checking against that 0.02, for example, I would say, oh, I'm going to check against something like this divided by 1.1, or thinking that it's that it needs to be smaller than this value, or you could also, I mean, it's sort of equivalent, but approximately like zero point 0.9 of the 0.02. That's one way of doing it. The other one is to say, okay, no, I'm going to compute what is the required ix's that I need to limit to this level, and then I say, well, but that's without p delta. I'm going to multiply those moments of inertia by 1.1. So it's like, if there was no p delta, this moment of inertia would be enough. Because there's p delta, would be 1.1. Having said that, it's not going to be really 1.1, because that usually happens when we have a very flexible structure. So most likely it's going to be a little bit smaller. But now you have like three different ways of thinking about it. You can use that equation with a slightly larger force, and it would be like 10% larger force. Another way of thinking about that is like the moment of inertia, you need to increase them by 10%. Or the other is that you limit the displacement by which you're comparing by 90% of that value. They all should, give you how you approach this in that preliminary design. Mm-hmm.